A difference of squares pattern, it looks like this. A to the power 2 minus b to the power 2. A squared is a square, b squared is a square, and we're taking their difference. We're subtracting one from the other. And we can always factor that in this following form. A to the power 2 minus b to the power 2 is a plus b times a minus b. So this is the key formula if you're looking at a difference of squares pattern. You can always use this pattern. And where does this pattern come from? Well, let's just check that this makes sense, okay? So let's use our box method to multiply this out and check that we have the right answer. A plus b, a minus b, multiply that out. A times a is a squared. A times negative b is negative ab. B times a, same thing as ab. And b times negative b squared. We add this all up. A squared plus ab minus ab minus b squared, and we notice that ab and minus ab cancel, leaving a squared minus b squared. All right, and this was exactly what we got when we multiplied a plus b times a minus b. So these are equivalent expressions. So let's use this pattern to factor these examples. So we start with x to the power 2 minus 49. Okay, so we have two terms. We're subtracting one from the other. The first term has a power 2 in it. And the second term, we might recognize this 49 as 7 to the power 2. So x squared is x to the power 2. 49 is 7 times 7, or 7 to the power 2. So we have x squared minus 49. It's x to the power 2 minus 7 to the power 2. And we use our perfect squares pattern, x plus 7 times x minus 7. This is our factorization. The quadratic split up into two linear factors. Let's try 100 minus x to the 6th power. So what's going on here? This looks a little bit different than the last one. We got the number in front, the constant term is in front, and the variable term is at the end. That's not a problem, really. So we can still just look for squares. So 100, we want that to be a square, and x to the 6, we want to see if that's a square. And because we have the minus sign in here, if those are squares, then we have a perfect, or a difference of squares pattern. So 100 is just 10 times 10, so that's 10 squared. And x to the 6th, well, anytime you have an even power, like this 6 is even here, you can divide that exponent by 2, so make that into a 3, and then pull the 2 outside. X to the 3rd power, you raise that to the 2nd power, that's x to the 3rd times x to the 3rd, 3 plus 3 is 6. So we can always realize even powers as perfect squares like this. So now we have 100 minus x to the 6th. This is 10 squared minus x cubed squared. And this is a difference of squares, so 10 plus x cubed, 10 minus x cubed is our factorization. And the last one here, 4x squared minus 9y squared. Okay, so now we've got a coefficient on both terms and two variables, but that's also still possible as long as they're perfect squares in both terms. We've got two terms and a difference. As long as they're perfect squares, we can factor. So 4x squared, can we write that as something to the power 2? Well, if we take the square root of 4, we get 2. Square root of x squared is x. 2x to the power 2, that's 4x squared. 9y squared, again, if we take 3y times 3y, because 3 times 3 is 9, we get 9y squared. So now we can factor using the difference of squares pattern. This is 2x to the power 2 minus 3y to the power 2. So our difference of squares pattern, 2x plus 3y, 2x minus 3y is the factorization we need.